Testing, testing.
I hear you.
Oh, you do?
Why don't I hear myself?
Oh.
I bet I have that muted. Go Bears.
Nice.
Test. Good morning, everyone. Welcome back. As soon as you're running, Ryan, can you get Zoom running over here? Oh man, hold on. That thinks we're over here. Is that where we actually are? Okay, sorry about that. A few technical problems. Go ahead, Ryan, don't worry about it. But we're kind of back. Let's hope things run for us. Last time we were talking about entropy, and what we found was it was a statistical phenomena, and it was only a statistical phenomena. That is, it didn't depend on the energy of the system, and that's quite remarkable. This expansion into of a gas into a vacuum, that happens spontaneously, and it stays that way. And we said it goes that way and stays in that state because that's the overwhelmingly most likely state to see, because there's so many combinations of that state. There's only one, essentially, relatively, there's one way to have them all on one side and spread out over the entire system. There are so many ways to have that arrangement that the one where they're all on one side is just statistically overwhelmed. You just don't see that state in nature because the other states are so much more likely. We said you had to have motion. You had to have random motion for this to be the case. That is, one fixed state of spread out over both boxes has the same entropy as one state in this box. So in order for entropy to be correct, you have to be, all these states have to be accessible. That is, the system has to have enough energy to get to them. And we said that's true because the energy wasn't any different between having them over here and having them over the whole area. So as long as you can access as long as all the states are accessible with the energy that you have, you'll spread out into all of them. But the state you observe is the most likely state because there's so many more combinations. There's so many more ways to express that state. We looked at the deck of cards and we said the same thing. This stacked up state is an accessible state, and spread out over the room is an accessible state. But that's only one of the accessible states in the room, and this is another accessible state in the room, same energy. But just spread out and just stacked, one spread out state and one stacked state have the same entropy. One way to do it, their entropy is 0. Those cards have to be flying all over the room or all over the floor to make that more likely to be in that over the floor state. So we said, that's great, but it's hard to count all those states. So it'd be nice if we could relate that to a thermodynamic parameter that we can easily measure. You'd hate to have to count up 10 billion states. You could try naming them or counting them out. You could go, I don't know, you could go person, man, woman, camera, TV, and just try to keep naming them until you got to all of them. But that would be incredibly hard when you get lots and lots of states. What is the way to name them? Or what is the way to thermodynamically access them? We did a a chem quiz based on this, and we said, what are the entropies of these various states if they are allowed to switch back and forth? There's 4 ways to do this, and if they're switching back and forth between all those 4 ways, that's higher entropy than this one state. And this, there were 6 ways to rearrange that state, and if they're rapidly switching in between them, then that is a higher energy state or a higher entropy state than that state. Again, if it's just one fixed state of 2 over here and 2 over here, and the same 2 stay over here and the same 2 stay over there, then that also has the entropy of 1, and there wouldn't be a difference. You have to access and you have to exchange between all your equal energy states in order to calculate a statistical entropy, in order for entropy to have an effect on the system. But we said, what's another state or what's another process that's spontaneous? We said that if a state has these accessible microstates and it moves towards that most probable state, and that most probable state overwhelmingly dominates the system, that's a spontaneous process. Entropy increases in the universe, and that's the time arrow for the universe. The universe moves towards increasing entropy. Delta S for the universe is greater than 0 for every process. It can be equal to 0 in the specific case of a reversible process. And we'll talk about that reversible process again, that one special case where the entropy of the universe doesn't change. A process occurs, but delta S for the universe is 0. Special case of reversibility, and we'll talk about that a little bit more. But here's a process that we know happens, and the direction of the universe is for that ball to bounce and hit the ground, and then not bounce quite as high and hit the ground, and eventually come to a stop. That's the natural progression of things. That's the spontaneous direction of things. How does that relate to our statistical interpretation? Well, we saw that the heating up, because of the impact of the ball, that caused the floor and the ball to heat up a little bit. It's a tiny little bit, and that extra states, that higher energy, the more accessible states due to the higher energy, is the statistical nature of that that process, slowing that process of the ball slowing down and coming to rest. So the extra states are those states of random motion of the molecules in the ball and in the floor. And that we know represents heating of the floor. And heating is a thermodynamic property. So there is some correlation between the statistical nature of entropy and a thermodynamic parameter that we can measure, namely the heat. And we said we never observe, this is the process we always observe, we never observe the ball sitting on the floor and suddenly a low entropy state occurs where all the particles are moving in one direction and they impact the ball and send it flying up. That never happens. That's where the system suddenly, the universe suddenly became more ordered and the ball took off. Now, we use that term ordered from time to time, and that's the term you have used maybe before. If you studied entropy, you said the cards on the floor are a disordered state and the cards stacked were an ordered state. And that's not entirely wrong. It's just the disordered state, we understand that now. It's not one arrangement. The disordered state is the fact that I can access all these states are accessible, and there are gazillions of them. If there are a gazillion of them and they're all accessible and the system can move in between them independently because they're all either equal energy or the system has enough energy to access all of them, then that is an increase in entropy. This state where we suddenly have concerted motion, we reduce the number of accessible states because everybody's going in the same direction now. I can't access all the other translational states. That's a decrease in entropy, and that would send the ball flying up, and we never see that happen. But it is related to heat, and that's important because the random motion related to heat also makes hot bodies and cold bodies, when they come together, heat flow from the hot to the cool. And we can write this down. What we're looking for, I'm not going to derive that or any more complicated mathematics than that, but to say that relationship that we're looking for between the statistical parameter entropy and the thermodynamic parameter heat looks like this. If you can define a reversible pathway and take the reversible pathway between two states and measure the heat divided by the temperature, that is the change in entropy. So now we can relate a thermodynamic parameter we can measure to a statistical parameter that we know drives the universe without having to count every microstate. And I'm going to do a little bit of math here, but I just want to get to a result. I'm going to do the math for the sake of maybe some of the people who are desperate to see some math in this class. If I look at this condition here, where I went from a hot object to a cool object, the amount of heat leaving the hot object is minus Q. The amount of heat entering the cool object is Q. So it's the same magnitude of heat, but here I've put the minus sign because it's leaving the hot system and it's entering the cold system. We could say that, well, the entropy of the universe, we're going to take that to be our universe for the time being, says that the sum of those two things is always greater than 0. And that's going to be true because here you divide that fixed number by a big number, the hot, and here you divide it by a small number, the cooler temperature. So this is for fixed temperature. If I want to look at the entropy change for a process where the temperature changes, I can say, well, let it change by a tiny little bit. And that's what I do here. The reversible process is just a tiny bit. If you go just a tiny bit in one direction, you can go just a tiny bit in the other direction. And that's kind of the 0 case in entropy, just a little bit here. And I don't perturb the universe enough that I can't go back. So go a little bit forward, a little bit back, infinitesimally forward and back. And you know, once I say infinitesimally, I'm going to do some calculus. You don't have to do any calculus in this class. But if you let the temperature change just that tiny incremental amount due to the heat involved, you can replace the heat evolved by the heat capacity times the change in temperature. We know that's how heat flows. And then you can add up all the tiny temperature changes, all the heat capacities and the heats divided by the temperature changes. And you know that if you integrate 1 over T dt, you get natural log of T2 minus T1. So you don't have to know any of this part in the middle, but you should be aware that if a temperature changes, you can still calculate the entropy by heat capacity of the system times the natural log of the final temperature over the initial temperature. So that's our result we're just going to accept. I did a little calculus because it's neat and it's fun for people who know it, but it's not ever going to appear on an exam or anything, just the result. So let's let a gas expand, be compressed, sorry. Let's let an ideal gas be isothermally compressed. Isothermally compress it. What is the change in entropy in the surroundings? So think about that for a minute and we'll take a vote. How many votes? Okay, so what were you guys thinking there? Let's have a look at Ryan's computer if we can.
Oh man.
That might be have to do with our.
This is fine.
Okay, we are just spread out over all of the possible options. So let me tell you what I'm thinking. So we isothermally compress the system. Now we're compressing. If it's isothermally expanding, we know that happens for free. No energy changes. That's the process that started all this whole discussion. If we isothermally compress it, then we had to do work on it. And if we had to do work on it and the temperature stays the same, then that energy we're imparting by the work has to go somewhere because it didn't change the temperature of the gas. So where is it going? Well, it's leaking out into the surroundings. And if energy is leaking out as heat into the surroundings, then the surroundings are absorbing heat. And if the surroundings absorb heat, then the surroundings entropy increases. So that's good. The entropy of the entire universe, both the surroundings and the system are in the universe, and the entropy of the universe is increasing. And now we know this is an interesting point. When we compress the gas, we reduce the number of microstates the gas could occupy. If you have a larger volume, you have a larger number of microstates. We reduced the entropy in the system. So that means this entropy in the universe, in the surroundings, had to be bigger so that the overall universe has an increase in entropy. If that process is a spontaneous process. If it's not a spontaneous process, that is if we force it to go, which we very likely could have forced it to go there, then that doesn't have to be true. So that has to be true of a spontaneous process. In this case, greater than 0. Well, now we'll just do the free expansion of the universe, and I'll just walk you through this. This is very interesting as well. So let's do that free expansion against a vacuum now. So you isothermally expand against a vacuum. What is the entropy change in the universe? Well, there's the expansion. Well, we know that the entropy increased because I had an isothermal expansion entropy increase. Remember, that was the only thing that we could find increasing in the isothermal expansion. That's what started this whole discussion. Why does it go and stay in that state? Why is that the natural direction if energy doesn't change? System energy, surroundings energy, nothing changes. It goes that direction because it never goes in the reverse direction, because that is the direction with more microstates, with a greater entropy. So if you did the calculation, you would say, well, it's isothermal, so no energy change. The heat is equal to the work, but the system didn't do any work, so the work is 0. Therefore, the heat is 0, and that means the surrounding entropy has to be 0. I didn't ask about the surroundings, though. I asked about the universe. And the system is in the universe, so that system increase in entropy is sufficient that the universe increases in entropy. I guess I write that down. System increased, surroundings not, system does, so universe does. Okay, let's look at this statistical versus thermodynamic entropy one more time. We're saying entropy is the number of microstates that are consistent with a macrostate. That is, a macrostate has sufficient energy to access all the microstates, so any one is possible. So any one of the gazillions of microstates for an ideal gas are accessible, and it's going to access them all randomly, and that's what leads to our statistical understanding. But let's try to link that with thermodynamics one more time. We've done it through the heat. Let's do it through our understanding of increasing temperature and volume. So here's a system, and it has accessible states. And we can treat this kind of like the particle in the box case. So the total energy is here. And that means these three states are accessible to the system. And it can be a mixture of them. Say there's if you'd like, say there's 100 balls in there and they can equally distribute among the states. Let's do the entropy. We would say if the entropy is going to change, we would take the number of final states minus the initial states and get an entropy change. So it's also true that if I measure the heat along a reversible path at constant temperature, I can get the entropy change. These two things should be the same. So let's do a temperature change though. Here are my accessible microstates here at temperature, at energy E. If I increase the temperature, there they are over there. If I increase the temperature, what happens? Well, the overall energy, if I'm talking about an ideal gas, goes up. So increase the temperature, that energy goes up, and look what happens. More microstates are accessible. I have this much energy, now I can get to all those energy states if I want to. So all of those are consistent. Oh, maybe I don't get that many of my particles up here, but that's accessible to me. So I will spread out over all those states and have a higher entropy. We kind of saw that in an ideal gas. We looked at when we increased the temperature, we saw that Maxwell-Boltzmann distribution, and we saw, oh, these high energy states suddenly become accessible. There's some particles that move very, very, very fast. So if we talk about just the states being the number of velocities I can have, the number of speeds I can have, then I can have more speeds, and I'm distributing the energy over a greater number of speeds. That's an increase in entropy, and that's represented here. Well, what about that change in volume? We were talking about the change in volume giving me more microstates. Is that consistent? Well, let's do that. There I have my number of states accessible increasing, W increasing, and the temperature increasing. So I could do my temperature thermodynamic analysis. Let's increase the volume. So here's my state again at the same conditions, my accessible states. Now I increase the volume. And now we got to go back and think, when you increase the volume, let's talk about it as a particle in the box. When I increase the length of the box, what happened? The energy differences between the states got smaller and they compressed together. So an expansion also gives me more microstates accessible. So that number of microstates, the energy of the system didn't change. It's just the configuration changed to give me more accessible microstates. So that also is an increase in entropy. So we have this beautiful now understanding of thermodynamics, accessible states, how changes in parameters affect those accessible states. If the system can get more accessible states at a certain energy, that is the higher entropy system. And we're saying that's the way the universe goes. The preferred direction of the universe. The time arrow. I like that time arrow word or phrase. Let's look at a system or a situation that we understand, because we've talked about it now, phase transitions. And the cool thing about a phase transition is it is the quintessential constant temperature process. We said when you change phase, the next joule of energy, once you get to that boiling point, the next joule of energy goes only into that change in potential energy. So heat is being absorbed at constant temperature. We can do Q reversible over T, indeed, because T doesn't change. So we'll look at the gas liquid phase change line, and we'll say, if I look at the standard state enthalpy of vaporization, and I look at that versus boiling point, and we've done this already for different substances, it turns out that those the entropy can then be related to the standard enthalpy of vaporization over the boiling point, because the heat evolving or being absorbed, depending on whether we're evaporating or condensing, is the enthalpy of vaporization, and that's happening at a constant temperature. So that's a clever point to get a very well-known thermodynamic parameter associated with this entropic statistical parameter. I'm going to start calling them all thermodynamic parameters now, entropy and enthalpy. Just because it's statistical doesn't mean it's not a thermodynamic parameter. And we find that if you plot this, and we did this before, we understand if you have a higher enthalpy of vaporization, you have a higher boiling point. And that makes sense to us. If you have to put more energy in to vaporize, a higher temperature, you have more particles that have that energy of that kinetic energy to escape the system. So this we expect to be more or less linear. It reflects the intermolecular forces. Greater intermolecular forces means I have to go to a higher temperature to get enough kinetic energies to break those intermolecular forces and get into the gas phase. So that we kind of understood fairly well to be the case. So this line is representative of the enthalpy of vaporization over the boiling point. So that ratio is a constant ratio with temperature. And for most substances then, it is a constant. That ratio is a constant, so that's a straight line. That is really an interesting thing. The enthalpies of vaporization of products are widely varied, but the entropy of vaporizations are about the same. And we kind of expect that. We kind of expect that because the relative order of the liquid system, the number of ways microstates of the liquid system, is much lower than the number of accessible states in the gas system. And in general, we're always going to say that gases have higher entropy than liquids. So if I have a high entropy state, an obvious high entropy state, and a low entropy state, those two states are independent of any energetics. I'm saying if you're packed closely, you have low entropy. If you're expanding into a gas, you have high entropy. That comparison is independent of the nature of the particle. And that's reflected here, that entropies of vaporization are all about the same. Is there a question?
Yes. Why is temperature in the denominator in the entropy equation if higher temperature correlates to higher entropy?
The question is, why is temperature in the denominator in this entropy question if higher temperature corresponds to higher entropy? We did see that a couple slides back. Increasing the temperature increases the accessible microstates. This equation here just says, how does the entropy change if the temperature doesn't change? Q reversible over the temperature at which that process occurs. Once you allow the temperature change, we go to that other expression, Cp ln T2 over T1. So there's a difference in whether I have a constant temperature process or a process where the temperature changes. So let's let's look at this. What is the enthalpy of vaporization for water? Is it less than this 90 typical number, equal to that typical 90 number, or greater than that typical 90 joules per mole number for vaporization of other substances? This is going to take some intuition, and I hope you're gaining that intuition, but I've shown you here the hydrogen bonding network in water. So liquid water, because of the strength of its intermolecular interactions, has a kind of a constrained liquid structure because of the strength of the intermolecular interactions. How does that reflect in the entropy of vaporization? Think about that for a minute and we'll take a vote. Okay, let's come back together. We're having a technical difficulty with me getting into a Zoom room here. I have to run up and grab my iPad or something, which sucks because actually that's the most fun for me, is getting to talk to you guys. So I'm feeling very isolated here, as I'm sure you guys feel isolated as well. That's why we do this, Zoom, so you don't feel so isolated while you're watching the lecture. So let's see what you're thinking. Ryan will show us the, oh, I unplugged it. Ryan will show us the result, and everyone is thinking, over half of you thinking C, that it's greater than that. When you uploaded, Melissa, when you uploaded the slides, I'll go back to my display. When you uploaded the slides, does the slide you uploaded look like this? Because it doesn't matter. I have a couple of versions. In this version, the answer is right there. Water has a greater entropy of vaporization. Why is that, is, I guess, the question. Well, this is why. It has this strong hydrogen bonding interaction. What does that mean? Strong hydrogen bonding interaction, an unusually high enthalpy, an unusually high enthalpy of vaporization. So the enthalpy of vaporization of water is up here at 40 kilojoules. And we said that was anomalously high. We saw that when we plotted this in the past. At 100 degrees C, that puts, oh, I think I can draw right on it. That puts the entropy of vaporization, the enthalpy over the temperature of boiling, off this curve. So that enthalpic effect folds into the entropic effect, because the enthalpic effect is the heat over that constant temperature. But there's another way to think of it. The purely entropic argument. If water does have those relatively strong hydrogen bonding, and that constrains the number of microstates in the liquid. So liquid water has a naturally lower entropy than most liquids because of that constraint. But gas is gas. That has about the same entropy as all other gases. But you're starting from a lower state in entropy in liquid water. So naturally the change is bigger. So we have this beautiful now deep understanding of both the enthalpic argument, how enthalpy factors into the entropy, and how the number of microstates factors into the entropy at the same time. Very satisfying for me. So the liquid has unusual order. The entropy of the liquid is lower, but this, for most liquids, the liquid entropy and the gas entropy don't very much over substances, but for water, that one does. And that increased order and that higher enthalpy of vaporization put you off that line. Fantastic. So we had standard enthalpies of formation. We can have standard entropies of formation. It's interesting that in enthalpies of formation, we picked this relative and arbitrary point. We said we'll call 0 the elements in their standard states, and we'll measure all the enthalpies relative to that. We can do that, but it's relatively arbitrary. We picked the 0, so we have relative delta H of formation. Entropies, there is an absolute 0. There is actually a 0 in entropy. That 0 in entropy is the ideal crystal, the perfectly organized crystal with no defects at 0 Kelvin. We can never achieve it. We can't get a crystal with no defects, and we can't get to 0 K, but it is a possible state. So we can say, just because we can't get there, as you know, we've done this many times, just because you can't get there doesn't mean it's a thermodynamic thing we can't consider. So this is the 0 in entropy, and it's a real 0. So if I say, well, what's the entropy, what's the molar entropy out here for the gas or something? Well, I just add up all the entropies it takes to get there from 0. And you know, we can do it now. We can take entropy changes from the solid to the liquid, and we know that's a temperature change. So we can use ln(Cp delta T and get that entropy change. And right here where we get to the melting point, that's a phase change. And that's a phase change at constant temperature. So we can use Q reversible over T, get the entropy of fusion, and then take the liquid and heat the liquid up and do Cp delta T, now the heat capacity for the liquid, get to the boiling point, and then take the enthalpy of vaporization, entropy, I'm sorry, I think I said enthalpy, entropy of vaporization, and then go to whatever temperature we're interested in the gas. And when we get to there, that's the absolute entropy of that system. Absolute because it's relative to a 0 that is absolute. So that is difference between 0 and here, the molar entropy of that state. And I did not put the delta because that is actually a number relative to 0. Can't have any below it. So you can plot them out. You can go tables here. And now you notice I have enthalpies of formation, and I formally put that delta in there, signifying that I've arbitrarily chosen the state, and these states are all relative to each other. These states are all relative to the same thing, the absolute 0 point. Not sure I wanted to say anything else about that. Oh, I see here the molar entropies are different. Obviously, liquids are farther down here, so they have lower entropies. The gas, we know that's the difference between the gas and the liquid, and this is standard, so it's the gas at 1 atmosphere, our standard state. And you can see entropies of gases do have slightly different values, which we know is okay. It's especially those tiny gases where the other states, the accessible rotational and vibrational states, are different. We're not going to go into that in any detail. But I can do the same old thing. I can say if you do have a process, so now I do put the delta in, the difference between reactants and products, I take their absolute molar entropy of the reactants, subtract it away from the absolute molar entropy sum of the products, and I do the usual machinery to get a enthalpy change for a reaction. Entropy change for a reaction. My goodness. Oh, that's all I have to say about that. So let's continue and just continue tracking this entropy of the universe. So the triple point of water, ice, liquid, and vapor are all in equilibrium. Which transition involves the greatest increase in entropy? The solid to the liquid to the gas, or the gas to the solid? I think we know this one. We'll just talk through this together. The greatest increase in entropy, solid to liquid. That's along this line where all the solids change to liquids. Liquid to gas. That's along this line, but I'm going liquid to gas. And gas to solid is that. If I want to do a greatest increase in entropy, then I have to do solid to liquid, because that's the ordered state to the more, the state with the more microstates, ordered to disordered. These are all the opposite direction. Oh no, I'm sorry. Liquid to gas is fine. That's a order to disorder transition. Gas to solid is not. That's the opposite. So I can see those are the same. Here's solid, liquid, gas. And liquid to gas is okay, but there's liquid to gas was that one. Why am I drawing that line now? There. Oh, I said greatest increase in entropy. This one's an increase in entropy, solid to liquid, but this is a larger increase in entropy, liquid to gas. The gas has the most microstates. When you go solid to liquid, you go from completely rigid to the liquid state, which has a little bit more microstates accessible, but liquid to gas, that's microstates of the constrained liquid to the spread out over the room, that has the greatest increase in entropy. But that begs a question. why are they all equally at the triple point? Why are they all in equilibrium? How come all of them exist? Isn't one of them favored by the universe when you look at this? So we're back to scratching our heads. We thought we said we have a time arrow for the universe. This is the greatest, this one is the most favored by the universe as far as we know here. What about these other processes? And why doesn't the gas just be completely favored overall? Why do we ever have solids and liquids? Well, we know it has to do with the temperature of the system, and we have this idea that it has to do with other energetic things in the universe. At the triple point of water, the universe is indifferent to which state I'm in. The liquid to gas transition, the gas to solid transition, the gas to liquid transition, all those transitions are equally likely. And that's bothering us because the entropies are different. Well, why is that? Well, one reason is we're talking about just the system. We have to talk about the whole universe. So the universe is disturbed more, the surroundings are disturbed more by that system, by those changes. In fact, someone came up to me one day and asked me, well, why are our bodies allowed to grow? That's a decrease in entropy. We're a very ordered system. Why do we grow? Why isn't that a violation of the second law of thermodynamics? And I said, well, no, because you're focused on just the system, me growing. In order for me to grow, I eat foods and I spew out carbon dioxide and water, gases in huge amounts. So I am disordering the universe in a crazy chaotic way by eating. So I, as a system, I can get a little more ordered because I am increasing the entropy of the universe in a dramatic way. I have to look at the big picture for entropy. So let's look at the big picture here. Here's water liquid. And I know when I go to water gas, I have to add energy. Delta H is going to be positive. And if I go to the solid, that's the endothermic process. So the exothermic process. I absorb energy endothermically to go to the gas. I release energy to go to the solid. Entropically, I also increase entropy for the gaseous system. And entropically, the entropy decreases for the liquid to solid transition. So why are all these things that appear to be disparate in thermodynamic space, how do we reconcile that? What it appears is that none of these states is energetically favored at equilibrium at the triple point. So they're not thermodynamically favored, they're at equilibrium. The universe is indifferent to whether you, as a solid, go to a liquid or to a gas. Or from a gas, it's indifferent whether you go to the liquid or the solid. So these pathways are all in equilibrium. So there's something else in there, and that something else in there, you would say, well, what if it's as if I took the entropy term and took the opposite sign. And if I took this entropy and the opposite sign, and then I scaled it appropriately to balance this other thermodynamic property, then you can imagine, oh, these things are going to cancel out. The enthalpy and some combination of the entropy, negative entropy, is going to give me a state where all these things are thermodynamically equal. And what is that state? So now I can go back and forth to either one because I've said there's some combination somehow of enthalpy and entropy that are in perfect balance at the triple point. And the universe is indifferent to which state I'm in. Go ahead, any state, I don't care. Do it. There's that process happening again. I'm sorry, guys. What I have in here are my other drafts of that slide. Is what you were seeing there. Didn't pull them out. In fact, am I going to do it again? Okay, no. So let's track the entropy for this individual step, the liquid to gas equilibrium. So liquid to gas equilibrium, I'm going to take the entropy of the surroundings and the entropy of the system to get the entropy of the universe, and that has to be 0. Oh my, this 0 needs to be over there. That's a little error in the slide. So we know this to be the case. If this is going to happen, the system and the surroundings entropies have to add to something greater than 0 or equal to 0 at the exact equilibrium point. Well, this is a little annoying because I have to track the entropy of the surroundings. And the entropy of the surroundings is essentially the rest of the universe. So if I have to track the entropy of the surroundings, I'm in a little bit of a conundrum. How do I capture that? It's hard to count the microstates of the rest of the universe. Well, we've already seen that entropy of the surroundings change by the heat evolving from the system over the temperature. So in this process, that's the enthalpy of vaporization over the boiling point. So the surroundings is intimately affected by what's happening in the system, and those two things have to be greater or equal to 0. So this is a state of kind of awesomeness because I have two system variables. I can concentrate on just the system, yet track the entropy of the entire universe. And the entropy of the universe is what I want. That has to be greater than or equal to 0. Greater than for a spontaneous process, equal to for an equilibrium process. So I am totally psyched. So I'm going to multiply through by negative t here. If I multiply through by negative t, that changes the sign there. You have to reverse greater than or equal to when you multiply through by a negative. And this quantity, h minus t delta s, delta h minus t delta s, encompasses the entropy change of the universe. It's a beautiful thing. Two system variables telling us about the entire universe, predicting spontaneity just by looking at the system. And it's 2 state functions, 3 state functions, the temperature. So that means this thing is a state function. So I'm going to give it a name. I'm going to say that is delta G. Delta G will be the free energy of the system, the ultimate predictor of spontaneity. I'm getting chills. It's so exciting. So delta G, I'm going to define as delta H minus T delta S. And that is, there's that thing we needed. We needed the entropy of the system to change sign, and we needed it to be scaled by the temperature. So that scaling of the entropy by the temperature is that missing piece. That's what made the entropy that negative thing that balanced out the enthalpy. So a beautiful thing here. We call it the free energy. And that's my favorite thermodynamic parameter, free energy, because it's such a beautiful description of the entire universe in a compact sense. It has to be In order for something to be spontaneous, the free energy has to be less than or equal to 0 in the case of perfect equilibrium, where the universe doesn't care which state, liquid or solid, or liquid or gas, I'm in. Oh, it's so much my favorite state that I named my boat Free Energy. Cool name for a boat because it's a sailboat, and the energy from the wind is kind of free, and you get to use that free energy to move your boat around. We have some pictures of that, I think. Oh, there they are. So here are your student instructors out on the boat on the San Francisco Bay, having a good time. I'm almost always taking the pictures. Here's Christine, and here are Melissa and Ryan on the boat. Here I am driving. I have a bad one there. Here is Free Energy 5, the little sailboat. So here's Free Energy parked in front of the house. Here's the little sailboat, and this is a movie. Wonder if I can play it. They're just sailing the boat in front of the house, just bringing it in to dock in front of the house. I might have the same shirt on. No, it's different days, different shirt. Different Cal shirt. They're all Cal shirts. That's fun. So Free Energy 4 and Free Energy 5 there. Let's go back to what we were talking about. Free energy, clearly my favorite thing in the universe. I hope it becomes your favorite thing too. And by all means, come to Berkeley. We'll go for a sail and experience that as well. So we call this thing the Gibbs Free Energy. That's where the G comes from. And we define it. Delta G is delta H minus T delta S. For the spontaneous processes, that's less than 0. And we saw why, because it's the enthalpy minus this scaling factor times the entropy that gives us the free energy. So I'm downhill is the spontaneous direction in free energy. This is great because we've been saying I can go up exothermic or endothermic. I can go up in entropy or down in entropy. I can go to the higher microstate system or the lower number of microstate system. Free energy for the spontaneous process always goes down. Spontaneous processes can be endothermic or exothermic. And we saw that with the dissolving of those salts. We said, well, that salt dissolves and it gets hot. That other salt dissolves and it gets cold. That didn't tell us whether the process was spontaneous. We couldn't have just said, well, I know it's exothermic, so it'll happen. Because I look at the other one, it's endothermic and it happens. We know it's the combination of some factor of T and the entropy to make a new thermodynamic function that's always downhill for the specific process. And we know how it happens now. If you're going to roll uphill, if you're endothermic, then there better be a T times a delta S that also increases. And that's counterintuitive for a minute because you're saying, wait, both of those are going uphill. But remember, there's the minus T. So if entropy increases, I take minus T and go downhill. And that leads to overall downhill for the free energy. And of course, if it's exothermic, in order for it to be spontaneous, it better be going to more order in the universe, because I got to multiply by minus T and cancel that out to keep that going downhill, delta G. I can then take the those parameters, and of course, if these two are the standard states, then I can get a standard state free energy change. And that standard state free energy change is just a fixed difference in free energy between all the reactants in their standard states, 1 molar, 1 atmosphere, 25 degrees C, pure solids and liquids present, to the products. And in delta G, the products are always down here for the spontaneous processes. Any delta G's up here do not happen. All the delta G's down here happen. And they are saying, well, if I have 1 atmosphere, 1 molar of this, and it goes to 1 atmosphere, 1 molar of that, this one is the favored state of the universe. That's the favored direction. That's the way the universe wants to go. And if I tabulate free energies of formation and standard free energies of formation of products and reactants, I can do the same old thing and get a difference between the standard state products and reactant states. So let's just look at this. We've looked at this up and down thing. Let's look at it one more time. So I could define something called free energy space. I keep doing this to you. I introduce different spaces, PV, PT. Now I'm going to introduce HS space, the entropic component and the enthalpic component. And I'm going to say, well, if a process is endothermic, that is, the system absorbs energy, yet I go to a more ordered system, the entropy decreases, then I'm in this quadrant of that space. And in this quadrant of the space, that is not going to happen for any temperature. That's never spontaneous. And when I say, what do we mean any temperature? T right here is the variable that will affect things. If my free energy isn't favorable at some temperatures, well, if this T gets big and this negative component gets big, then maybe I can overcome the enthalpic unfavorable part and get my delta G to negative. Can never do that here because delta S is always negative and T is always positive. So negative times positive, that's always a positive component. It's entropically unfavored. It doesn't matter if you're endothermic or exothermic. Well, if you're exothermic, you'd go sometimes. You'd go at low T, and that's this case here. Exothermic and less order, well, I'll get to that case. If I'm exothermic and less order, so I am exothermic, delta H is negative, delta S is positive, I'm in the diagonal component quadrant over there, that happens for every temperature that's spontaneous because the enthalpy is helping you go to lower thermodynamic state, it's negative, and the entropy is helping you. Entropy is positive, but it's multiplied by the negative T. You're going to less ordered system. It's scaled by that negative T. Those are spontaneous at all temperatures. And of course, there's the other combinations, exothermic and more ordered. And that's this quadrant here that happen only at low temperature where delta S is positive. So you need a big T to get the whole thing negative. And endothermic and less order up there where the higher T is, the bigger this component is. And even though this one's positive, the minus T delta S eventually overcomes it, and you get a delta G that's negative. I thought I had some examples of those. Thought there were some demos here, but let's do this. What is the standard enthalpy for the reaction shown, which is spontaneous? I'm telling you, it is spontaneous at 25 degrees C. What's the standard state enthalpy for this reaction? And this reaction is NO2 single monomers, NO2 monomers, going to dimers, them coming together and making N2O4, both in the gas phase. Let's think about that for a minute, and we'll take a vote. As soon as that's captured, I'll go back to the set of 4 were captured, Ryan. Yes? I'll put the set of 4 up there for you to enjoy. Think about that for a minute. We'll come back. Okay. You seem to be coming to a conclusion here. Finish up your discussions. We'll give you another few seconds to get a vote. While you're doing that, I'll go over to Ryan's computer display. Oh, she's already got it done. You already stopped the poll. 90 responses. A, the most popular. So A, you're saying this is a spontaneous process. The A's are saying, oops, be careful. That's not the button I want. That is. Here's an interesting thing. Let's consider all the answers. This, I'm thinking about doing this. If you're watching this at home by yourself, you're watching and you want to practice chem quizzes, part of the chem quiz is you're talking to each other. So you have to consider everybody's argument. You might have to consider an argument for each of the answers. So let's just do that as an exercise. Let's consider the arguments. So first argument is delta S has to be less than 0 since the number of particles decreases. So it must be exothermic to be spontaneous. Okay? That's the argument for A. That sounds reasonable. Since delta S is less than 0, the number of molecules, the number of particles is decreasing. We saw that. It's going from monomers to dimers. So that is fewer microstates available to the system. There's just fewer particles. Entropy is an extensive property. The more you got, the more entropy you got, the more microstates are available. So yes, if you're going to decrease the number of particles, you're going to decrease the entropy. Well, what about B? Spontaneous reactions do not release or absorb heat, so delta H is 0. Is that actually the definition of a spontaneous reaction? No, the spontaneous reaction, delta H can be positive or negative. Delta G has to be negative. C, bonds are formed, so it must absorb energy. Well, let's I hate that one. If I form bonds, I always release energy. So these are made up things. Obviously, you would reject that one out of hand. You would reject that one out of hand, and you would say it must be A. So, doing these on your own, maybe you live in Turkey and you can't watch in real time, you would do this. So, we do have our friend Alpin watching from Turkey. I hope you're here today, Alpin. What time is it in Turkey? It's like 8 hours or 10 hours difference. But yeah, 6 p.m. He's making the effort to watch. I love that. In fact, there's someone in Moscow and someone in New Delhi, or so. There's people all over the world who are actually enrolled taking the class. So
So 7:15 p.m.
Alpin is responding
7:15.
in real time. Hi, Alpin, 7:15 p.m. where you are. Yeah, we already decided what the answer is. That goes to, there's a decrease in entropy occurring. So if there's a decrease in entropy, then minus T delta S has to be negative for it to be spontaneous. So if delta S is less than 0, T delta S minus T delta S has to be greater than 0 for it to be spontaneous. That means delta H must be less than 0 for it to be a spontaneous process. It has to be exothermic, or the disadvantageous part, the decrease in entropy, would make it unfavorable. Delta H, it has to be exothermic enough to overcome that entropic component. I have a demo of that. I'm not sure why it's not here. Okay, boiling water. Okay, now you're getting into the things that you know you're going to see on the exam because you know me now. I'm going to have you look at plots, and I'm going to have you tell me something about them. So I'll walk you through this one together. What's the correct plot of the standard state free energy versus temperature for the reaction water liquid goes to water gas? Very simple physical process, a phase change. So a physical phase change, liquid goes to gas. What is the correct plot? Does it look like this? Does it look like this? Does it look like this? They're all linear. And I hope you would expect that they would be linear. Why would you expect that they be linear? Well, delta G is standard state, delta H standard state, minus T delta S standard. These things are constant. They are a fixed set of values. We can find them in tables. They don't change with T. Delta T does change with T. T is T, that's changing. So delta G is a linear function of temperature. It's y equals mx plus b kind of action we're going here. So we have a slope and an intercept. The slope is determined by delta S. The intercept is determined by delta H. So they're all linear. The question is, where's the slope and the intercept? Well, positive slopes look like that. Negative slopes look like that. Okay, so you go downhill. That's a positive slope. That's a negative slope. That guy has a negative slope. Slope is determined by the sign of delta S. Liquid going to gas, what is the sign of delta S for that in the standard state? Well, liquid water at, first, what is the standard state? It's the difference between liquid water at 1 atmosphere, 25 degrees C, 1 atmosphere of total pressure, at liquid water. The liquid doesn't have a pressure in its to itself. It's liquid water present with 1 atmosphere of gas above it at 25 degrees C. That's the standard state. It's not a state that we normally observe. You don't get 1 atmosphere of pressure of gas over water at 25 degrees C. It's this artificial standard state. to which we compare everything. But either way, going from liquid to gas, that's an increase in entropy. Delta S is positive. So if delta S is positive, what's the slope of that line? Well, there's a negative sign in there, so the slope has to be negative. Delta H, we know delta H going from the liquid to the gas. That is what? Endothermic. I have to absorb. So delta H is also positive. So I need positive delta H, positive intercept, negative slope. I hope there's only one that does that. Yes. Negative slope, negative intercept. Positive slope, negative intercept. Positive intercept, I don't see it. The intercept is up here somewhere, but it's positive. And a negative slope. You can see, you can already tell that's something that Kubinec's going to love because there are no numbers. And I had to guess, I had to give some kind of, I had to do all this conceptual stuff without one single number to get to a conceptual answer. I had to know the expression. I had to understand what these things mean. And I know everybody is going to, in discussion, is going to be going, go over that again. Do go over it again till you understand it. Here's those three explanations. We'll go through that. And here's the explanation written out again so you can see it. A gas is produced, so delta S is positive. It's endothermic, so delta H is negative. The slope is negative because there's the negative T there. So I have to have a negative slope. The slope is negative there and there. So B is out from that argument. The intercept has to be positive. The only one with a positive intercept is that one. The free energy of boiling. What is the standard free energy difference at the normal 1 atmosphere boiling point of water at 100 degrees C? The standard state free energy difference for boiling water at 100 degrees C. Bigger than 0, equal to 0, less than 0. Think about that for a second, and we'll take a vote. yeah, stop it. Don't show the histogram till we say, let's see what you're thinking. That is the cue. Okay, so you've had some time to think about this. This is Ryan's slide. Why don't you move that thing into the middle there, Ryan, so we can all see it. I think the farther it over to this side, the better it is on the live stream anyway. So,
man, I think it's bad everywhere.
okay. So about 90 responses. Let's see what you're thinking. We're thinking that the standard state free energy difference between those two things is 0 at 100 degrees C. I wonder if the standard state made a difference for you guys. Let's talk through it. So we're saying we're at the standard state. So we're at the case where we've already been able to plot it, delta G versus T, standard state versus T. The boiling point is where you have 1 atmosphere at 100 degrees C. And that's what we said we had, right? That was the question. I think it was. So the liquid gas equilibrium point, that's where we are. The standard state difference, 1 atmosphere, becomes an equilibrium state if you go to 100 degrees C from your 25 degree standard state. You can actually think of the standard state at different temperatures. And you can do that because delta H and delta S aren't very strong functions of temperature. But don't go crazy over that. So yes, I'm at the liquid gas equilibrium. That's what you guys were saying to yourself. That is an equilibrium situation. The equilibrium situation is where the free energy difference between the products and reactants is 0. Where did I put the pen? Here. So I am right here on this plot. At temperatures above that, where would I be? Temperatures above that, delta G would be negative. And when delta G is negative, which side is favored? The reactant or the products. And that makes sense. Higher temperature, the gas favored. If I'm at lower temperatures, delta G for that difference between the products and the reactants, the delta G of the products is less than the delta G of the reactants in the standard state. So delta G is negative, and that intimates that at lower temperatures than the boiling point, it would go back towards the liquid. Delta G is 0 there. So here they are all plotted out. We have standard state enthalpies of formation, standard state free energies of formation, standard state entropies of formation. Notice the difference in magnitude. Entropies of formation are joules per Kelvin mole. The enthalpies and free energies are kilojoules per mole. So the entropy effect is small per mole, but I multiply it by the absolute temperature in Kelvin, and that's when it starts to have an effect. So entropic effects are not very big at low temperature. As you would expect, everything is the number of microstates available at low temperature, everything else being equal, is always smaller. So here's a giant table of them. I don't know if I was going to point out anything in particular about that. So there it is. There it is again, apparently. So we can look at examples. We'll stop and we'll look at the examples tomorrow. Here's some demos of this actually happening. And this is review. We're just going to look at examples of the sign of delta H and how that affects the sign of delta G. So it's the same as that free energy space. And in fact, since we're running a little behind, and this is just looking at Lonnie doing demos of these things. Oh, well, one of them is cool.
It's just on the next slide.
Let's just do the cool one, which is the ionic. Yeah, and that one is the top one. Let's just look at the cool one because it's fun, and we'll go out with a bang. So here's a reaction. We already seen it. Alkali metals in water. Okay. And we can predict everything that happens here. We already know it's exothermic. So we already know delta H is negative. We can see from the nature of this thing, we produce a gas and we started at liquids and solids. So delta H absolutely positive. That means we're in that situation. Delta H favors delta S being negative, or delta G being negative, and delta S favors delta G being negative because it's minus T times that. So delta G is negative for all temperatures. So we can look at that. Lonnie did it in lab, but these crazy nuts did it everywhere. So let's just see that. The reactions of alkali metals in water. I might, if I can. I don't have the settings accessible here. I was trying to, I was going to go at twice speed. So there's lithium reacting in water. That's kind of nice. We've seen that one before. Sodium reacting in water. And we know how the ionization energy changes, not quite as exothermic. Pop, pop, pop. It'll probably jump out of there, though, eventually. There's a nice explosion of the sodium. We'll see the explosion in slow-mo. There is, oh, that wasn't that slow-mo. Okay, here we go. Dropping a drop of water on powdered sodium. Yes, boom. What will happen if we dump, here's what you always want to do, a huge chunk in water. So we're going to go to a lake, chuck the sodium into the lake, and huge chunk. Let's, oh, yeah, there. Spontaneous at all temperatures. You could have thrown that in a frozen lake through the ice. It still would have exploded. Spontaneous at all temperatures. But these guys go nuts. Here's potassium. Oh my goodness, yes. Even more exothermic. And rubidium, we know we're going down the periodic table, easier to ionize, more exothermic. A huge chunk of rubidium in water. They do that one outside in the bomb area. Cesium in water. This is even more exothermic. This one shatters the glass. A large volume of it. Let's do it, guys. Let's do it. Yes. Cesium exploding. We love Lonnie, but Lonnie didn't go to this extent to entertain us. Francium, they're going to talk about francium for a minute. You can't do francium. Its stable isotope has an half-life of only 20 minutes. So we don't have any stable francium. But they're just saying that's what that might look like if that reaction actually occurred. So there we are. Spontaneous at all temperatures due to the increase in entropy and the exothermic nature of the reaction. We'll pick up tomorrow with equilibrium processes. We did like it. Are we clear?